Okay. Well, on to week 2 of online classes. Freak out. Today we're going to start with 12-1, Estimating Limits Graphically, page 736. Now the reason I like to do chapter 12 first, before chapter 11, is because typically chapter 12 takes more time and it's more of a heavy focus because chapter 12 is actually calculus, or at least we get into calculus, so it helps you build into whatever college potential program you may go into. Or also chapter 11 is a lot of probability and statistics, which we've covered before, so usually your guys' background's pretty solid. Okay. So first we need to talk about, obviously, what calculus talks about. Calculus has two main problems. One is if I have a graph, let's say I need a graph then. If I have a graph, just any old graph will do. My first problem is calculating an equation that will be tangent to a given point. Now, not tangent as in SOHCAHTOA tangent, tangent as in it hits it at such an angle, like if I were to hit this right here at an angle, I would only touch that graph at one very specific point, and I would actually also be perpendicular to that equation. That's what I mean by tangent to a given point. Okay. The other problem that calculus focuses on is what is referred to as area under the curve. Now that is typically designated as between the equation and the x-axis. So let's say if I were talking about, again, like roughly this point. Calculus wants to focus on solving all the area from that point and bounded between the axis. So all of this that is under my equation curve and between my x-axis. The y-axis also serves as sort of a boundary line. So calculus focuses on those two type of problems. The best way that we have figured out to solve those type of problems is what are called, well, limits. Now we've talked about limits before, way back in August, maybe September, way back in section 1-3 or so. So again, we need to really focus on what is a limit. So let's see, where's my good eraser? That one makes a mess. So limits, what's the formal definition I got for limits? It's where if f of x approaches specific values, unique value L, from both sides. So, I shouldn't have erased my graph. Oh well. I need to redraw a graph. You probably don't need to redraw a new one. If I have a graph, and if I wanted to find the limit of, let's say, 4, so my limit as x approaches 4. And then I would type in whatever my equation is right here. Let's just say f of x for now, because I don't know what my equation is. I need to show that whatever my value is, I'm approaching the same value from both the left and the right direction. So in this case, I am, therefore my limit would exist. So let's get right into it. Example 1. Yep. Example 1. Estimate limit where, let's see, so my equation would be as x approaches 2, so the limit as x approaches 2 of negative 3x plus 1. Okay. So we're going to estimate the limit as x approaches 2 of negative 3x plus 1. Now there's two ways we can do that. We can do it graphically, so I can draw a graph. So, shoot on my blank. If I draw a graph, 3x plus 1, well that's in slope-intercept form, so we can just draw that. My intercept would be 1, and I would have a slope of negative 3, 1, 2, 3, over, and my limit would be something like this. Or my graph would be something like this. And I can estimate graphically at the x is 2 mark. Well, this is 0. This would be not quite. So if at 2, negative 3 times 2 plus 1, negative 3 times 2 would be 6. Negative 6 plus 1 would be negative 5. So negative 5. And I can see that my function is continuous. It's just one line, and I'm approaching it from the exact same value on both sides. Now that would be graphically. We can also do it numerically. Now, numerically is the one we did a ton of way back in chapter 1. As soon as I draw it, you're going to remember and you're going to be groaning. So I get x, and I also get f of x, and then I get 7 boxes. Let's see. One, 2, 3, 4, 5, 6, 7. I remember my x are my x values, and I'm obviously going to test 2, so 2 is going to go in my middle. Okay. F of x is whatever I get after I input x into my function. F of x is whatever it spits out. Now I need numbers that clearly get up to 2, so we used 1.999, 1.99, and 1.9. Inversely, I need numbers that are bigger that slowly get down to 2. So 2.001, 2.01, and 2.1. Now all I gotta do is start typing those things into my equation. So negative 3 times 1.9 plus 1 gives us negative 4.7. 1.99 times negative 3 plus 1 gives us negative 4.97. 1.999 times negative 3 plus 1 gives us negative 4.997. 2.1 times negative 3 plus 1 gives us negative 5.3. 2.01 times negative 3 plus 1 gives us negative 5.03. 2.001 times negative 3 plus 1 gives us negative 5.003. And in this case, I actually can plug it right in because there's no restrictions. Remember, restrictions be something like if I had 1 over x, I couldn't plug in 0. Or if I had something like the square root of x, I couldn't plug in a negative number because we don't use imaginary for limits. And then we obviously can't ever divide by 0. So there's no restrictions here, so we should be all good. 2 times negative 3 plus 1 gives us, again, negative 5. Okay. So we can show, well, first of all, let's take a look at our values. Negative 4.7, negative 4.97, negative 4.997. Clearly I'm getting closer and closer and closer to my negative 5 value. And then from my other side, negative 5.3, negative 5.03, and negative 5.003, I am clearly also getting closer and closer to my negative 5 value. So here I would say my limit does exist, and the limit as x approaches 2 of negative 3x plus 1 equals negative 5. Now, moving on to example 2. This one's a little more cut and dry because it's pretty easy to see all that stuff. And it's easy to one to graph. I'm going to keep graphing them. I'm just going to take a while to graph them. Just because I don't have every graph memorized off the top of my head. And they're not all going to be linear. So let's see. Example 2. Again, we're estimating limits. So let's estimate the limit as x approaches 3 of x squared minus 9 all over x minus 3. Okay, I'm going to take a quick second here to graph it on my calculator. That one's kind of cool. That one actually is relatively just a line. Okay. Now the issue though is I get this. And those of you who remember way back when, that would just be a hole in our graph. Shape hole. And that hole is at x equals 3. Well, looking at the equation, why is that hole in our graph? Well, one, the big thing is I can't divide by 0. If I have an x equals 3, I would get 9 squared minus 9 is 0, but I would also get 0 over 0, which just isn't allowed to happen. But my real question is, what was my limit as x approaches 3? As we see, we're approaching relatively the same value. So my limit exists, it's just my point at that limit doesn't, which is still okay. And then we can get right into just doing it numerically with our grid. X, f of x, one, 2, 3, 4, 5, 6, 7. Okay. So again, this one's always easy. It's whatever I'm testing. My test value being 3. Now I need stuff that's smaller and lower respectively. So let's see, 2.9, 2.99, 2.999. 3.001, 3.01, and 3.1. And now all I have to do is check my values. Now the cool thing is because I already graphed this, I can actually cheat code it a little bit. If I go to menu on these, I guess if you guys don't have these, probably never mind. We'll just do it the old-fashioned way. So I get 2.9 squared minus 9. That would give me up top a negative 0.59 all over 2.9 minus 3, which would be a negative 0.1. So I get negative 0.59 divided by negative 0.1, which would give me it should just be 5.9. Okay, 2.99 squared minus 9 divided by, well, I would get a negative 0.01. Negative 0.01, which would give me 5.99. As you can see, a pattern's really starting to emerge. My next one's going to be 5.999. Now if I do it on the other side, 3.001 squared minus 9 divided by 3.001 minus 3, so 0.001 is going to give me 6.001, then 6.01, and of course 6.1. Okay. So we see that, again, both values, or both directions, are going towards the same value. Here I'm going towards 6, and here I'm also going towards 6. So my limit is still 6. Just because I can't plug it in because it doesn't work, because I would get 0 over 0, does not mean that the limit doesn't exist. It means it's not a function there, it's not a continuous function, but the limit still exists. So limit, as x approaches 3, of x squared minus 9 over x minus 3 equals 6. The next thing we're going to talk about are left-handed and right-handed limits. So we get left-hand limits focus on the approach from the left. If you were just talking about the limit, the left-hand limit, as x approaches c from the left, you will have a c, and then you'll have a minus sign up where the exponents normally would. That just means you're approaching it from the left, from the negative values in theory if you're approaching 0. If we're doing a right-hand limit, we are naturally approaching from the right. Okay. And again, my nomenclature, how to express that, the limit as x approaches c from the right, well, if left was a negative sign up top, the right is a positive sign. Okay. So the big thing that we've been doing so far have been two-sided limits. For a two-sided limit to exist, the left limit has to equal the right limit. So essentially, limit as x approaches c from the left has to equal the limit as x approaches c from the right, which is what we've been showing this entire time numerically with our boxes approaching it from the left and our boxes approaching it from the right. Okay. On to example 3. The limit as x approaches 0 for the function absolute value 2x over x. Now again, there's a couple ways I can go about doing this. The big ones being, again, graphically and algebraically. If I were to graph this, and I were to start plugging in values, I would get a very interesting graph that would look like this. If the big thing is we can all see that x is 0 is not going to work because I'd be dividing by 0, right? So I'm going to have a hole in my graph. And I actually have a separate one where I have a hole in my graph here. Because what the goofy thing that happens is if I have an absolute value, is how this will work. Let's say I picked x is -3. I get 2 times -3, which would be -6. What's the value of -6? Well, that would just be +6. So I'd get +6 over -3, because that was my x value. So I get +6 over -3, so my answer would be -2. So what happens is all my negative x values, which are all these ones right here, would actually end up with a function that is just -2. Well, inversely, on my positive ones, it would just be +2. So I get something weird like this. Now, if I were to focus on the limit as x approaches 0 from the left, the entire time, all the way to 0, I'm at the value of -2. And that would work too if I did it numerically in my boxes. Again, all these values are -2. But if I were to do the limit as x approaches 0 from the right-hand side here, all these values until I got to 0 would all be +2. Now they don't have to be that exact value to be that limit, as we showed earlier with like 5.9, 5.99, 5.999, approaching 6. This one's pretty cut and dry. If they're all 2, it's approaching 2. It's not moving, it's committed to that spot. So here, we would say that our limit as x approaches 0 from the left is -2. Our x as approaches 0 from the right would be +2, but our two-sided limit and overall the limit would be a d and e. It does not exist. There's not a limit as x approaches 0 from both sides, because naturally -2 does not equal +2. Example 4. I'm going to call this one unbounded. Sometimes we get situations where where limits aren't exactly finite. They're kind of unbounded. So the limit as x approaches 4 of 1 over x minus 4 squared. Now again, I'm going to start with graphing. I'm using my calculator. Remember, you guys, I guess I forgot to mention earlier, if you ever want to look at a graph and you're at home, remember you can just go to Desmos calculator, or desmos.com/calculator. Or Google something like desmos.com graphing calculator, and it should be like the first thing that popped up. So you can always check your work on a graph. Sorry, I forgot to mention that before. Okay, anyway, I'm going to graph this, so just hold with me for a second. So I have 1 divided by parentheses, x minus 4 parentheses squared. Okay, as I thought. So my graph is very interesting. It actually looks like this. And funnily enough, this point right here is our 4 value. So, again, I can look at it graphically first. So, I would look at my left-hand graph and see that I'm slowly approaching positive infinity. And here I'm approaching, again, positive infinity. I have no bound. So if I were to just look at it graphically, the limit as x approaches 4 would be infinity. I can also, again, do that numerically, which we're going to do with our boxes. So my test value, pretty easy, 4, then I get 4.001, 4.01, and 4.1, 3.999, 3.99, and 3.9. Okay. So I can just type in some of those things into my calculator. Calculate, let's see. 3.9 minus 4 squared would give me 0.01, and then I get 1 divided by 0.01 is going to give me 100. Then I get 3.99 minus 4 squared would give me 0.0001, so 1 divided by 0.1230 would give me 10,000. And then 3.999 minus 4 squared, 1 divided by 1, 2, 3, 4, 5.0 is 1 e to the 6th, so I get 6 zeros, which would be 1 million. 4 doesn't work because 4 minus 4 would be 0. I'd be dividing by 0, so I know that value doesn't work, which again makes sense because if I look at it graphically, does my function ever get to a point where I can do it? No. We have, back in the day, we used to have these, we called them asymptotes. Same thing happens. That would be an asymptote. And the actual same pattern works on the other side. I get 100, 10,000, and 1 million. So here, my limit actually doesn't technically exist. My limit doesn't have a value because for a limit it has to approach a certain thing. However, we still can technically say the limit as x approaches 4 is infinity, even though infinity isn't necessarily a definitive answer or a number in this case, or in any case. Example 5. I'm going to call this one oscillate. So we also get some interesting interactions, specifically with the trig functions of sine and cosine. So if we have something like the limit as x approaches 0 of cosine 1 over x. Now again, I encourage you to graph it just to see all the craziness that's going on. And I just need a quick refresher. Let's see. Trig cosine 1 over x. Okay, so the graph's actually kind of cool. And you might have to even zoom in to really check it out, but it looks like this. No, that's not exactly what it looks like, but it's a lot more fun, so I kind of continued it for a while. We get this very back and forth pattern called oscillating, just bounces back and forth. Very, very rapidly and very, very quickly between two values. Okay. Now, it's very to estimate the limit if we go in each direction because the oscillations back and forth so badly. In fact, depending on what you're looking at, it's going to bounce between 1 and -1. As you can see, this is -1, this is 1. It's bouncing back with that so quickly that the limit does not exist because, again, it's happening so rapidly that it's so hard to follow that path, or if we do it algebraically, that each value would essentially jump back and forth. So we treat that as a limit that does not exist because of oscillation. Very, very fun one to draw. Okay, let's see. Oh. So the problem with limits is the limits have some issues. So for limits not to exist, one of three things has to essentially be true. If the left limit does not equal the right limit, the limit doesn't exist. If left or right approaches plus or minus infinity, the limit doesn't exist. For limits, we just want one numerical value. Or, in that last case, there's oscillation. Now, again, oscillation, I'm not talking about something like this. I'm talking about where it's so rapidly that you can't even tell almost. So this wouldn't be oscillation because it's slow enough to where we can find the values, even though it's bouncing between two of them. With this type of oscillation, it's so rapid, it's not even worth mentioning. So again, this is oscillation, this is not oscillation. Or at least in the specific terms of us having a limit. This would have a limit. Okay, and then I have one more thing to talk about, and then one example. Okay. So, finally, we've only been doing limits where we're approaching from both directions. We can technically also do limits at infinity, but not where limits equal infinity, limits at infinity. So we had a very specific name, but let me draw it and let's see if you guys can remember on your own. So if I have a graph, let's say for the sake of argument, 1 over x, because that's what we're going to use our example. Okay. This one looks like this. Very classic limit. When I'm talking about the limits at infinity, would be something like as x approaches infinity. So for example, what pattern's happening as we go this way? Or if we're talking about the limit as x approaches negative infinity, going this way. Okay. Those of you remember that it has a very fancy name called end behavior. That's the big thing with limits at infinity, that's just those end behavior things. So, let's say, example 6, limits at infinity. And we do f of x, let's do limit as x approaches infinity of 1 over x. And remember that the same process would work the other way. Now, if we're only doing one direction on our box, we only have to include the one direction. So f of x So if we're going to positive infinity, we achieve some numbers, some easy ones. 10, 100, 1,000, 10,000, and then, I don't know, 100,000. You want to pick numbers that are so far spread away that it's easy to tell you're going forever. You don't want like 1, 2, 3, 4, 5. They're too clustered together. You don't get an overall perspective on the entirety of the function. So my numbers are all pretty spaced apart. Now if I were to type this into my calculator, I would get, again, 1 over 10, so 0.1, 1 over 100, so 0.01, 1 over 1,000, so 0.001, 1 over 10,000, 0.0001, 1 over this, so 0.00001, etc. As it's going, we clearly are approaching 0. We're getting closer and closer and closer to 0, we're never quite getting there. So my limit, as x approaches infinity of this, would be 0. The exact same way that my limit as x approaches negative infinity would also be 0 for this particular function. Okay. So again, I know this one was a pretty long one just because there's a lot of examples, but hopefully most of it's reviewed so you guys remember. It's just been a while. Thank you for listening, and I hope you guys all have a wonderful week.